Hi everyone, welcome to Lesson 7. This is our last lesson in our Trigonometry Part 2 unit. Today we're going to be solving trig equations using identities. Before we get to it, we're going to start with this opener question. We have the value of n that makes the statement below an identity is, and remember an identity meaning left side equals our right side. So we want to find an n value where it's going to become a fraction over here, and that's going to equal this side here. So from previous lesson, what I want to do is work with one side and leave the other side alone. I'm going to leave that right side alone there. I'm going to basically try my best to clean up and get just a cos x denominator on the left alone. Well, right now I have two fractions, so what I want to do is combine fractions. The way I combine fractions is make a common denominator. So in this case here, I'm going to have a common denominator of cos x and the 1 plus sine x. So if that's my common denominator, that means I'm going to take this original 1 plus sine x and multiply it by the denominator of the other fraction, which was 1 plus sine x. We had an addition sign in the middle, so it goes right here still, and we have our original cos x, and this is going to be multiplied by the other denominator, which is this bottom cos x here. I want to multiply this out to clean this up. This gets me 1 plus 2 sine x plus sine squared x. And then here cos and cos is going to make plus cos squared x. And our denominator is still the same, no changes there. And so I should write down my denominator cos x and 1 plus sine x. From here, I'm going to try to clean up as much as I can. I can't combine this 1 to anything. I have 2 sine x, which I can't combine to this sine x because this is a degree 2, this is degree 1, so you can't combine them. What I do notice is sine squared x plus cos squared x. These two here should have been right off of our formula sheet. This is our Pythagorean identity. Sine squared x plus cos squared x is equal to 1, so I'm going to clean that up. So I have 1 plus 2 sine x plus 1 now because these two were combined. That's combines to become 1, and we have our still cos x and that 1 plus sine x. From here, of course, collecting like terms, I have 2, so that's going to be 2 plus 2 sine x. All that's divided by cos x, and the 1 plus sine x still. And what I'm going to do next here in my numerator is factor out a 2. So if I factor out a 2, I end up with 1 plus sine x. Oops, that didn't work out. 1 plus sine x, there we go. And all that's still divided by the cos x, and you had that 1 plus sine x. And now finally we can cancel out our denominator and numerators 1 plus sine x, leaving you overall with 2 over cos x. So therefore n has to equal 2, because if you look back at your original question, it was n divided by cos x, and we were looking for just a number in the numerator. Our number is just 2, so therefore n is equal to 2. In this lesson here, so we have a few steps and a few tips that you can use to help solve trig equations using identities. The first trick here is to rewrite or to express each equation in terms of one trig function, if possible. So if you have all sines, that's good. If you have sines and cosines, you want to switch it over to either one. If you have tangent, I'd probably switch it to something like a sine and cos as well. Note that you're going to do a combination of substitution, reciprocal, quotient identity, Pythagorean identity, and double angle identity. It's any combination of this to basically isolate your equation. Check your solution for an equation that does not include the NPVs, so make sure that your answer doesn't include any NPVs. Also double check what your domain is, if it's restricted. If not, then give general solution, and of course verify by graphing. And you can also verify by using your graphing calculator by going y1, y2. In the first example here, we have solve the equation with this domain restriction between 0 and 2 pi, aka between 0 and 360 degrees, not including 360 or 2 pi there. So if we had sine x minus root 3 cos x equals 0, what I want to do is try to uh, isolate my trig functions. But from here, I can't isolate anything. There's nothing in common, so I'm just going to move it away, that cos x. So I have on the left sine x is now equal to positive root 3 cos x, because all of those, this is just one big term, was moved to the right. From here, I'm going to divide both sides by cos x, so now I have sine x divided by cos x equals root 3. Sine x, cos x, again, this is two different trig functions. I want to combine these. Sine over cos I know is just tangent, so I'm just going to switch that around to become tangent x now. Tan x equals root 3. And tan x equals root 3, this is something that we can solve. So if you did a quick sketch here, we're trying to find two quadrants where tangent is positive because we're positive root 3. Our two quadrants, of course, is going to be quadrant 1 and quadrant 3. And of course, if I can draw a triangle straight down there. Okay. We do want to eventually find this reference angle here and this reference angle in here. So let's find what x is equal to. So if you go inverse tan, so tan x equals tan inverse of root 3, x is then going to be equal to 60 degrees. So right away, I know in quadrant 1, we're equal to 60 degrees, and then in quadrant 3, we're going to be 180 plus 60, so we are at 240. And again, they wanted the answer in radian, so let's switch both of these over to radian. So 60 is the same thing as pi over 3. And 240 is the same thing as 4 pi over 3. And there we have it. This first one is completed. In example B here, we have 2 cos squared x minus 3 sine x equals 0. Right away, I cannot combine anything because one trig function is cosine, the other one's sine. But this cos squared x, I can probably switch out for one of my trig identities. If I look at my Pythagorean identity, cos squared x is equal to 1 minus sine squared x, so that's what I'm going to switch this out for. So right away, I have 2, and then I'm going to do a quick switch. This is the same thing as saying 1 minus sine squared x. And why did I do that? Well, now I have everything in terms of sine. Then we still have that minus 3 sine x equals 0. From here, I'm going to just distribute in. So this is now 2 minus 2 sine squared x minus 3 sine x equals 0. Rearrange. If I rearrange this equation, I'm going to basically move everything from the left all to the right. I want a positive whatever squared, and this right now is a negative. So if I rewrote this, I'd have 0 on the left equals a positive now 2 sine squared x plus 3 sine x minus 2. From here, you have your choice of solving for x. You can sub out all those signs and sub in just an x and then solve. You could have also, that's probably the best way to do this, because you could have then plugged it into quadratic formula, decomposition, or your graphing calculator, and all three methods would have worked. When I factor this by decomposition, I end up with something that looks like this. I have 0 equals, it's going to be sine x plus 2 and a 2 sine x minus 1. So those would have been my two factors if I had fully factored this equation. From here, I'm going to set each factor equal to 0. So then my first factor here, I'm going to end up with sine x plus 2 equals 0. So sine x equals negative 2. Of course, sine x cannot equal negative 2 because our radius only goes to 1 on a unit circle. Therefore, right now, we will have no solution here. Therefore, no solution. So no solution here on the left. Let's try this one here. This one, we have 2 sine x minus 1, which then equals 0 right there. We're going to isolate for sine x, so sine x is equal to positive 1/2. And of course that does exist. That's going to be in positive, sine is positive in quadrants 1 and 2. So I'm looking for an answer between 0 and 180 there. If I solve for x is equal to, which is the sine inverse of 1/2, is equal to just 30 degrees. And so there we go. In quadrant 1, I'm equal to 30 degrees. That's an equal sign, equals 30 degrees. And then in quadrant 2, because that's where else sine is positive, I'm equal to 150 degrees because 30 would have been my reference angle. So that's 30 versus 150. And again, we want both in terms of radian. So I'm just going to quickly rewrite both as a radian. And of course that is pi over 6 for the 30 degrees and 5 pi over 6 for the 150 degrees. In the next two examples here, we have sine 2x plus cos x equals 0. Well, we only have one option for sine 2x. That's our double angle identity. We only have one option to rewrite that, so I'm just going to switch it out. My one option is sine 2x is equal to 2 sine x cos x. Then we have this plus cos x still equal to 0 there. From here, I'm going to factor out a cos x to see what I end up with. So I have cos x. It's going to be factored out. And then we have 2 sine x plus 1 left over equals 0. I'm going to set both equal to 0 now. So I'm looking for when cos x equal to 0 and when sine x equals, well, basically that's negative 1/2. So that's my 2 that I'm looking for. Well, when cos is 0, you're at 90 degrees or 270 degrees. So x would have equaled 90 degrees or 270. And of course, again, this wanted us to rewrite everything in terms of radian. So 90 is the same thing as saying pi over 2. And 270 is the same thing as saying 3 pi over 2. There we go. On the other side here, if you solve for x, x is going to equal negative 30 degrees. We're looking for two sections on our graph that where sine is equal to negative. That's in quadrants 3 and 4. So if I have x equals negative 30, my reference angle has to be 30. So RA's reference angle equals 30 degrees. So in quadrant 3, x is going to equal 210 degrees because we are at 180 plus 30. And then in quadrant 4, it's going to be 360 minus 30, which is 330 degrees. And of course, we want to convert both of these into radian. So now we have x equals 7 pi over 6 and 11 pi over 6. There we have it. On this next example here, example D, we have sine squared x equals 1/2 tan x cos x. So we have a bit of every function right in here. So let's try to rewrite it so that we only have one function. So first things first, I'm going to get rid of that tangent. I'm not going to really do anything here yet on the left here, so I'm just going to leave that as sine squared x there. I'm going to leave that alone. This is equal to 1/2. Tangent is the same thing as saying sine over cos, so I'm going to go sine x over cos x. That's all multiplied by cos x still. Of course, I see numerator, denominator, cos x, those are just going to cancel out. And I'm going to get rid of this fraction by multiplying by 2 to both sides. So I'm going to go times 2 times 2 to both sides there. So let's quickly clean up and see what we get. Right now we get um, 2 sine x, or sorry, 2 sine squared x at least, equals, that 1/2 goes away because we multiplied it by 2. This is equal to just sine x. Okay, now we have everything in terms of just one trig function. That's perfect. I'm going to move that sine x over. So I have 2 sine x, or 2 sine squared x, that is, minus sine x is equal to 0. Let's factor out a sine x here. So we end up with 2 sine x minus 1 equals 0. Setting both equal to 0, what do we get? So on this first one here, I'm going to set sine x equals 0, and of course that only occurs at 0 and 180 degrees. So x equals 0 degrees and 180. Notice I didn't include 360 because we had a domain restriction earlier of from 0 to 2 pi, not including 2 pi. And of course this here, x in radian, is going to be equal to 0 and pi. Over here we have our 2 sine x minus 1. Again, set that equal to 0, so you have your 2 sine x minus 1 equals 0. So then sine x is equal to positive 1/2. And of course, where would that occur? Well, we are looking in quadrant 1 and quadrant 2 there. So x is equal to positive 30 degrees. And so if you know it's 30 degrees, your two answers should have been x equals 30 degrees in quadrant 1 and 150 degrees in quadrant 2. From here, converting both into radian, this is now pi over 6, comma 5 pi over 6.